My name's Kevin Nash. I'm the developer and designer of the NashFan. A little bit about my background. I'm a very long Corvair owner since the early 1980s. First car was a 62 Spider that had a 140 in it. Um, Next car as my daily driver now. I've owned that since the late 1990s. It's basically 6,000 miles a year since then, maybe 2 or 3 years down. That's a 63 turbo. It's been heavily modified. I got it when it was stock. It's just been worked on a little bit over the years. Um, when I graduated from high school, I started a vocational program to be a machinist. It's a year and a half long program. Um, I was always really interested in making things, designing things in my head. You know, being in the machine shop. I just loved it. Um, but I was always, technical, science and technical stuff. I just really liked, but anything that would have, that I would have been interested in college, I just wouldn't have gone to because of needing a math background. I absolutely hated it when I got out of high school. So it was kind of surprising to me how much math those guys got to learn in machining program. I literally didn't even know what trigonometry meant. To me, it just, he says trigonometry, and I was like, what? And I was thinking it was like calculus or something. Oh, so I just sucked it up and learned it, and discovered how much fun it was seeing it every day and using it every day, and felt like I just like had so much more control over my ability to figure things out. Uh, Near the end of the program, somehow I found out it's just like, engineers that know how to make stuff in the shop and like getting their hands dirty are pretty highly prized. And I'm reading this and I went, you're kidding. Engineers get to get their hands dirty if they want. Oh, it's like sign me up, And so right then it's like I had to start college the next fall, and be able to apply my abilities in the shop to do something else, And so I started college, and although it took longer than most folks that were planning on going to college, I got a degree in mechanical engineering in 1990, and but kind of in the business, ever since then. My favorite, best subject in college was fluid mechanics, study of fluid flow and how it impacts everything, and stuff that impacts the fluid flow. Uh, and just general interest in turbos and whatnot. It seemed like I was maybe the perfect person to try maybe taking on a fan design. Okay, next slide. My personal production fan. If it looks like it's a big giant turbocharger compressor to you, good, because that's what we were going for with this. There is not a hill of beans worth of difference between what a turbocharger is supposed to do, how it acts, and what affects it, versus a good centrifugal fan. Everything that makes a turbo work makes a centrifugal fan work, and vice versa. So everything that all the stuff that you do to get the maximum efficiency out of the fan was done to this, and it's for exactly the same reason that you do it on a turbo. Big difference is that I don't have it's too hard to get the inducers in along the front part of the blades like you would on a turbo, but that turns out to not be that big of a issue, as you'll soon find out. Okay, next picture. This is kind of a side view. You can see the forward lean of the blades. They do exactly the same as blade angle on turbos. the is what it does. It increases the efficiency of the fan. You get more velocity pressure doing that than if it was straight up. Has a lot less tendency to stall, and for what we're doing, it also somewhat desensitizes it to shroud gap. Next slide. Yeah. The why is something like this a really good idea? It's all about the very poor efficiency of the stock fans. I have to tell you, it was kind of a big surprise to me as to how inefficient the stock fans were. It's not a fan design problem per se. Any good forward curved fan, like the 1960, that's actually kind of a variation of it, but or a radial fan is supposed to hit 60 to 65% every single time. It does not have anything to do with how much resistance it faces or anything else. It's the and if the stock fans actually did that, I would have never even tried to it would have been so hard to beat that it just would have been almost senseless. So about that low efficiency, that was kind of a head scratcher for me because I thought it was just a fan shape. If it was a radial fan, then you're supposed to be able to get 60 to 65%. That was the end of it. And I didn't really understand that at first, but looking into it more, kind of found out about that. So what's good about the stock cooling system? Well, it's the big super overpowering advantage of having a centrifugal fan inside this open shroud is that it's generating a lot of static pressure, and that tends to even out the airflow around the head, everything. And the airflow distribution set up like this is really, really good, especially when you compare this with, if you know about the issues that have always seemed to come up with any vertical fan design, whatever it's put on, however they do it. VW's got all this weird vanes and crap and diverters and shit in the housing. That's to keep one side of the heads from getting about the same amount of air as the other side. One head always wants to run really hot with compared to the other one, so they retard the timing to that one cylinder. You know, anybody that's tried to make a change to that, they keep tweaking these blades a little bit, and all of a sudden one gets a little cooler, another one gets hotter. It goes on and on and on and on, and they've never actually fixed that, despite all this screwing around with it. Porsches, there's two cylinders that run hot on those, and you know, but a horizontal system, that's about the most even cooling you can get. And apparently a lot of the Porsche race cars went horizontal, and it was a lot of it was just because of that reason, that they could get this nice even airflow. I didn't actually know about that until just I thought there was only one car that had a horizontal drive on it, but apparently it went way back in time. So what's the deal with the efficiency? Well, so early on in the Corvair's development, when they were working on the fan and shroud, you know, they automatically went horizontal because that was just to give them a lot of clearance in there because they already wanted kind of a low roof line. So the when they were working on this, they went to a centrifugal fan because they said, oh, we won't be able to use an axial fan here, but the things are too noisy. And they shoved that off the table, didn't even think about it anymore. And then they went to the squirrel cage type fan, and then and they knew about this thing where if it's not in the blower housing, then the efficiency won't be very good. So they go and do the equivalent of that. These are called diffusers. They're blades that go around the outside of the fan. They direct this velocity pressure basically where they're aimed at, and it's every bit the same as taking a blower housing and aiming an exit in different directions around the fan. They did that right from the get-go. They knew they needed to do it for best efficiency, and something counterintuitive happened. The center cylinders all cooled the best. The corner cylinders were getting robbed of airflow. They cut these diffuser blades back, made them smaller, tried it again. The airflow distribution got better. They cut them back some more. It got better again. Finally, they just deleted them entirely, and that was how they got the best airflow distribution. And in fact, there's a fairly, if you look, there's a chart, shows how the temperatures of the various cylinders stay really close to one another until you get to the very end, and there's probably turbulence or something going on. It's at a fairly high RPM where that happens at. But they were stuck with this fan. That first year fan, the efficiency on that thing was only 16%. That shows you how sensitive that thing is to being in a housing or not. That is awful. So the next year, they went to the famous 61 through 63 fan, which is a good radial fan. They are a little bit less sensitive to efficiency, to being in this housing. And then because of the weight of the fan, inertia of that big thing, they went to the mag fan later on. All of those things are highly sensitive, not being in that blower shroud. So the rest of this is stuff that's about the setup on the cooling system that makes it so that the fan doesn't really get the output that it should. The intake is restricted. The original intake size was for an 80 horse engine. They went for about 1800 CFM. And then they never changed the size of it. But it's actually worse than that. When you put a pulley over the fan, you're blocking the inlet. A way of grading fans as far as how much intake flow you have is just to take the intake diameter and divide that by the OD of the fan. You'll come up with a ratio of like 0.71 to 0.75 to 0.65 or something like that. And it's actually the same thing as turbochargers. You know, an E-flow has a ratio of about 0.75, which is it's a real high flowing turbo. F-flow is a 0.65, and the little B-flow is a 0.55. But when you do the same calculation on a mag fan, it looks like 0.72, and it's like, Kevin, what the heck are you talking about? That's awesome. But once you factor in this blocked airflow that's from the rim of the pulley, just not the flat part in the middle of the fan that won't flow, it's the rim of the pulley that's sticking out over the fan. When you subtract that area off of the intake and then refactor it as a new circle of the same size, as though it doesn't have a pulley, now all of a sudden that ratio falls to 0.55, which is just like a B-flow turbocharger. To compare that with other engines, VWs have that same ratio as 0.65, which is like a flow turbocharger, you know? So there's like 10% wasted intake area, and that definitely affects the output of the fan for a given RPM. And then the pulley actually causes the air to come into the fan at a funny angle. It's more lateral and has to make a real sharp turn and go in. It's not straight down and turn like you'd think. It just doesn't do that. The next one is the fan to shroud gap is just horrendous. Mag fans have a fan to shroud gap of around 0.2 to 0.25 installed. This fan gap is like subtracting from the height of the blades. VW fans, as it happens, have a fan to shroud gap of 1/32. A way of seeing that and expressing it is the percentage of the blade height. Mag fans have a percentage of blade height is about 15%. VWs, it's only 3%. They're getting a lot more of their fan for the size than we are for ours. It makes an enormous difference when you tighten up that shroud gap. Talked to a guy that with a potted up 140, and he had a way of tightening up the fan to shroud gap to 1/16. He runs this thing around in hot weather on the street and with the lower shrouds on, and he just can't even believe how cool it runs. So there's a lot of stuff about the setup of the fan that came from the factory that really doesn't make a lot of sense. And there's one more thing. Late cars, particular, their intake area that they have on their just the grill is pretty small. It looks like it's only about half the area on the compared to an early the louvers on the early shroud. And where the intake is placed, there's like zero ram air. It's zero. On a early car, I measured it, and you actually get ram air from it, and it almost compensates for maybe not even having quite enough intake area on those. I know one guy put a manometer on inside his engine compartment on a late and wound it to 4,000 RPM. He was surprised to find that there was a pressure drop of 0.7 inches, which is crazy. If it was a fan engineer saw that, he'd say, fix that first. Don't worry about anything else, fix that first. It's like they consider that just a huge problem when it gets up around an inch. So, okay, next slide. The short history of the Nash fan. Right. The this sort of this fan design thing, we got SolidWorks work is probably in 2001, and I started wanting to try modeling more sophisticated things than I was doing through work, and having a Corvair and knowing about all the fan winding that seemed to come up every once in a while on message boards and stuff, the usual electric fan question, the usual radiator fan question, why can't we do this? Why can't we do that? Blah, 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 blah. I started, modeling a fan as mostly it started out as practice. As my modeling skills got better, the more it looked like a turbo, because those are the most efficient centrifugal devices on this planet, especially when you have to really make them work against pressure. And even after I got the design done, which is in about 2012, oh my, there was a lot of trying to figure it out before I got it on a car. There's nothing like testing a real fan on a real device at real system pressure to find out what you have. There, you cannot just take a mag fan, copy the blade shape on one and have it work for you. You'll be so far off wrong. You'll understand immediately why GM probably didn't want to do this. The reason is because it makes the fan too big. If this would have been a standard backward curve fan, it probably would have had a diameter of over 12 inches, and the blades would have been probably 2 inches high. It's got to be a monster to compete with the mag fan. So I knew there was, I made compensations into it. But there's nothing like testing one for real. And so there was a lot of time trying to get one made. And finally just held my breath and plunked down the big bucks for a couple of prototypes. Next slide. once I received my prototype, and because my engine was apart for doing some work, I was eager to find out how the fan compared to the mag fan. This was the easiest way I could get some numbers and a relative sense to how it worked. All this is the top shroud with the bearing, with a fan bearing on it, duct tape to the floor in my shop with the fan shroud duct tape to the floor in the shop. The pulley's mounted. It's got a piece of black tape along the rim to provide color contrast for a reflector, so I could measure the RPM using a laser tack. And then notch. Oh yeah, there's a hole in the top part of the shroud. This is a bolt hole for something. I can't remember what it is, but that's where the pressure probe goes in. So I was able to measure pressure and RPM for the fan. This is a great way to detect changes if you're going to do something to the system, like put a bell on there, change the intake diameter of the shroud. I'm seeing here, I'm experimenting with venting of the pulley to see if I could get more airflow out of it. And it's real easy to see these little tiny changes on the with this little bench tester. And I know at one point I actually had the bench set up to mimic system pressure on the car. Even though I was running these really slow fan speeds, it was as though I took a mag fan and slowed it down to 1200 RPM, whatever I was able to drive it with a Dremel tool. All this experimenting that I did on the bench, it showed me this, like, it was crazy how much I could change the numbers without changing the fan. Every single test I did showed that the fan was just crazy efficient compared to the stock fan. The one that was really interesting was when the more you asked the stock fan to flow, the more that poor Dremel tool got bogged down. You know, you're trying to drive this rim of the pulley with the little Dremel tool, and when I set the system up for, you know, lots of flow openings in the shroud and ran it that way, the mag fan it just dropped the RPM of this Dremel tool. It was kind of awful. And then with my prototype, it was like, it almost seemed like it was going faster, you know? And if I looked at the change in RPM between those two, it was like, oh my, there was like taking 80% more power for the, if I had to spin the mag fan up to be the same as or hit the same pressure as this Nash fan. I mean, this thing was acting like a water pump. It just didn't care about the pressure or anything. It would just had a certain speed that it could run at. The other thing that happened was I noticed that it was always taking more RPM to hit a certain pressure. This is how I could tell that it was probably down on airflow. I was kind of expecting that because of the blade shape and lots of compensations and stuff, but really neat that when I had this thing set up to simulate the stock resistance of the engine, the bench tester results actually, when extrapolated from those to the actual fan speeds, were really, really close to what I actually saw. So it was cool to see this. Next slide. This is how we did pressure versus RPM for the Nash fan with the airflow pulley and a bell mouth. That pressure curve is the green line, green curve, and this is done with the engine hot. I have to point this out because the original pressure numbers for the mag fan, as for all their fans, by the way, are done cold. This is no head heating, doors blocked open. That's how they get their pressure. When the heads get hot, the pressure is false, and this too is seen on the engine when it gets up to its head temperature that's supposed to run at. They had different depending on what they're doing. The exhaust from the heads might be as high as 180 in one test and down as low as 150 in another. But this lower curve, the red one, is what the pressures tend to do when the heads are hot. For example, at 4,000 RPM, you're supposed to see around 7 inches. When the engine is cold, you're supposed to see about 8.3 to 8.4. My testing that I did on the stock fan long time ago, before I did the prototype fan, they were coming out all exactly the same as what I saw on here. And then the thing about this lower one is it's being affected by stuff. The pressure curve is no longer parabolic. It's something less than a parabola. And I'm not sure quite all what it means, but efficient fans don't do that. Inefficient fans seem to do that quite a bit. They're more likely to let the heat of the engine push back and try to shove the air out when it's at low speeds, and then the air is more likely to make it through at high speeds. This is why it tips the fan curve over a little bit, so it's showing little bit less pressure than it should at that fan speed when it's hot. And then as you go down lower in there, it either doesn't lose pressure or it actually goes up a little bit. To compare this with the Porsche, the coefficient that they got, the exponent was 1.9 versus the flow. On a Corvair, it's 1.8. And as best I could tell with this prototype, it just didn't seem to have any. It was acting like a perfect parabola all the time. It was pretty crazy. But I don't know, like, if I was supposed to try to get the heads hotter or what. It was really neat to see it, and no evidence of stalling over the ranges that I was able to run at. One last data point that's not on there on this is that the fan hit about 14.5 inches at 5,500 RPM, which is pretty awesome considering that the stock, I could never get over about 11.5 or 12 with the stock fan, no matter what I did. Next slide. This is the efficiency comparison for the prototype. This is 61 through 63. Peak efficiency for this prototype was 56%, which is entirely perfectly normal for a backward curve fan. The two stock fans on here, they're already below 30%. And what's weird about it is that the efficiency is falling with speed, and it should be climbing just like it is with this other one. They're already working too hard. So you can see that there's a big difference in efficiency. One thing, I was happy to see this. This is what you're supposed to be able to get on average. I was a little disappointed with it because you're supposed to be able to get upwards of 75%. And the theory was that I wasn't pushing the fan hard enough. You know, it basically needs more static pressure, or, you know, maybe from more flow or whatnot to see its best efficiency. That was kind of, I was thinking if I resized the fan a little bit, that might be all it was needed to really get it into the big league efficiency. Next slide. And yes, this is inches of water column. Somebody asked that real quick. It's kind of standard pressure units for air systems. So these next set of graphs are going to be about the as tested, hotted up, all the tricks thrown at intake system. This is a bell mouth that's quite a bit bigger than the stock intake system. It's actually about intake ID of about 1.5 or 8.5 inches versus the stock intake, which is 8.125, and it has guide vanes on there. Lordy, I wish somebody would have told me that there might be some potential for air spin in the intake. It's there. It reduces the output of the fan a lot. Air's being trying to chase these fan cells as they go around, and it's can't get quite caught up until it goes in. And I seem to have gained just about as much airflow with this as fan systems that are about 30,000 times bigger than mine when they've had air spin problems. So it's just really neat to see that this basic idea works on everything. So next picture. Yeah, this I'm really proud of. This is showing some big league pressures. So at 4,000 RPM, this is 11.5 inches. The 61 through 63 fan will get to 10 inches here. The mag fan only gets to 8.4 inches. Look at this curve. There is no point on this curve that ever crosses any of the other ones. So there's so much pressure being jammed into the engine that the pressures don't change from heat because it's not letting the heads get quite hot enough. And what happens with my car is that there's so much pressure that the doors end up staying shut most of the, or not shut, they're open maybe quarter. So there's a whole bunch more margin when the when the heads start to get warm. The doors will open full, and then you'll start getting the maximum flow that you can. This is so crazy to see this kind of pressure. Peak pressure is reached. Instead of at 5,500 RPM like it was in the prototype, we're down to about 4,500 RPM. You know, this is big league stuff. Mine does start to, I've noticed that at even higher fan speeds, it does start to tip over a little bit. I don't know what that is. I wouldn't say that it's stall. I don't think it is, but even if it is, the easy thing to do if you need that extra flow is to, you know, take the lower shrouds off or something. The highest pressure that I've read with the fan is 15.5 inches. You know, this is crazy. You have to work so hard to get even close to that with the mag fan. I've heard of it being done, but they're just spinning the heck out of the fan. They have to neck down the inlet so that it keeps the fan from using a lot of horsepower to do it. So it's they're not even in the same ballpark. Next slide. The efficiency for this thing is also crazy, out of this world. It's 86% peak efficiency. This is just a little, it's actually really close to 4,000. It's almost right on 4,000, and that's just a sweet spot to be having your peak efficiency at for most cars. You know, and again, the efficiency for both fans is well under 30% there. To put this into context or comparison with other fans, all of the Porsche fans on the vertical drives for any of the stock cars is 71%. They will not get past that. It's just, that's the best they can do. They stall out and go down to 65% at the end of their effective range, and that's where they're max out their flow. The big thing about the flow on those is that the peak fan speed was always limited by how close to the speed of sound they were, and that's why the fan speed always ended up being, you know, about the same. It was started to get geared down towards the middle upper end of the RPM range, and not the cooling demands were down lower because of the enhanced torque and increased engine displacement. Their fans were geared. The smallest engine had a pulley ratio of 1.3 their last all air cooled engine, or mostly all air cooled engine, had a pulley ratio of something like 1.8. Compare that with our fans, 1.58 sounds to be pretty fast for a engine that only, between 80 and 100 horsepower. You can see why I was talking about maybe the fans are just running too fast because they're not efficient enough. The other fan that comes to mind is a VW fan, which is around 56%. So 86% is better than any other fan that I know of that's been used on an air-cooled engine. It's just truly special to see that. Next graph.
There is a question that I think I should read now,
Okay.
just because you're on that section. When you
Yes.
tested the temperatures on the cylinder heads as a result of the new fan, did you have cylinder heads that had the casting flash removed first?
Oh, yes, of course. This is all done on my heads. My heads are always well deflashed heads. I figured, I mean, they're not like as deflashed as some I've seen, but there's no obvious blockages in the heads. I mean, it seems like every time I take them off, I want to deflash them a little more, but all the big gains from casting flash were done a long time ago by somebody else. They're good looking heads. They're probably about as well done as any of the factory heads that were prepared for testing.
Okay.
You're welcome. Okay, this is what it's all about with this is pretty wild. The stock fan uses about 5,000 at 5,000 RPM is 15 horsepower. The Nash fan horsepower usage at that same RPM is 7. When you take the lower shrouds off, now the horsepower is 4.49 horsepower. If I had included that same thing on the mag fan, it probably would have been a good 20 to 30% higher. Never did it. That's one of the buggers about popping the shrouds off on, even if you need the cooling, it's going to use more power. And whether you feel it or not has everything to do with how tight you put the fan belt. The 7 horsepower at 5,000 RPM correlates with about 11 horsepower at 6,000 RPM. And that's the kind of horsepower usage that you can expect from the mag fan when you take the pulley ratio down to 1.25. That's a huge reduction in fan speed. It's removing a lot of cooling, also because of the fan speed. Neat to see this lowering of horsepower usage from flow. Actually, one of my customers verified this claim of mine. I tested it. I didn't really believe it when I saw it. I knew it was supposed to happen, but I still didn't believe it. He did it on his car. He put his car in a dynoed it with the lower shrouds on, doors open, Nash fan, bell, and airflow pulley and everything. And then he just took the lower shrouds off and ran the test again. And he said it dropped 5 horsepower, just like I told him it would, which is pretty crazy. Next slide. Okay. I want to talk about this tuning for different applications. Most of the lower horsepower cars, I would say, this is a ridiculous amount of output. They don't need it. We're using a stock pulley ratio right now because that's the easiest to do. It's easy, simple. The goal all along for me was to make a fan that was big enough that you could make a dent in heat for horsepower on turbos and other heat challenged applications. But for a 110, 80 horse, 95 horse, you really don't really need that much. In fact, the fan is so big when set up this way, you won't get stock pressures unless you run the pulley ratio down at like 1.42 to 1 is the same pressure at idle as you would get with the mag fan. And in fact, if you were going to go 1.25 to 1, say for really high RPM things, and you have the lower shrouds off, you're still more flow than you would get with the stock fan. It's about 430 CFM at a 1,000 RPM. So the other thing is that when you have a fan like this, you really got to start thinking about warm up, especially in cold weather. I really don't need to have this much output when the temperature gets down below 50 degrees. I mean, I'm serious. There were times when I drove 10 miles into town doing 45, 50 miles an hour, and the head temperature would not get off to 20. This is the doors basically shut. This is the lower shroud doors shut. The summer winter plates off. You know, that is crazy cooling for a air cooled engine. You know, it's fine warm up. You know, in terms of a water pumper, but Jesus, we're used to you know, 250 is being kind of halfway sort of okay warmed up, you know. So it's something I want to work on more. Got some ideas for it, maybe having some sort of actuators that are built into the shroud that can just open the door, open the cooling and just bypass that going into it. You know, if it's got some sort of real safety feature to keep that from happening when you don't want it. And for higher fan speeds, it's long known that our cars, the mule drive just doesn't like shock loading at high fan speeds. It's not really the fan speed itself that causes them to go bad. I've heard of guys going out well past 7,000 RPM with them, but it's when you downshift, speed up and slow down really quick. There's too much load changing from the tight side to the loose side and back again. I got a really slick idea about how to fix that once and for all. I'm tired of hearing about it. And all I know for sure is that other cars that have gone mule drive, they don't seem to have the kind of belt tossing problems that we do with ours, even under racing conditions. And it seems like the only thing they have in common with ours is that it's a mule drive. It's like everything else that could matter is different. You know, a lot of them will have the alternator not on the same drive as the fan drive, so that there's, you know, remove the inertia from trying to chase two different rotating things and having them get screwed up. Okay, next. All right. How do I get one? The only way you can get one of these is to participate in a group purchase. We're organizing the next run. Our goal is to start, you know, being able to get going on this next spring, and have these for ready for delivery late in the spring. But you can't wait for the fans to get made and then buy one. You have to put your money in and go along for the ride just like everybody else did. The process is this: you tell me that you're interested in being a part of this group purchase. I send you out this order form explaining the prices and the process and everything that goes along with that. You fill that form out, you send it back to me, and then the next email you get will be that we have the minimum number necessary so that we're going to start people to send money in. And then the long wait begins. Be patient. It's an awesome fan. Takes a long time to get. We've never had one of these runs go off hitch free. they always seem to take longer than we think, but when everybody is just thrilled to death when they get them and have been really happy with them. And by the way, we've already got repeat customers. We have customers from the first run that are already wanting to get more of them on this next one. And it's just really neat to see the excitement about it. You can buy the fan by itself. You can buy the fan with the airflow pulley kit. You can buy the fan with the bell, although the bell isn't really part of the run. I order these up through and have them 3D printed on demand, and either can ship them straight to you, or I can have them shipped to me, and then I do a little final setup on them, do all the work, send it out to you to eliminate hassle for you, and because I want to be a good guy and give service like that to anybody that wants to be a part of something like this. I do that for my customers now. If they want something, that I might be able to help them with, I'll just do it. There's no extra charges. Okay, one thing I can answer right now, the fans are 5-axis CNC machined. They're done by a really top flight aerospace shop in Southern California. It's really hard to find places that got mills big enough to even run this thing. It's a big monster of a mill that you need to be able to cut this cost effectively. Those guys that do machine turbochargers, they typically are these little tiny things that only make sense for little tiny turbo compressors, real ones, and just they physically don't have enough throw to do it, and even if they did, they're not really stout enough to do this the right way. And of course, these are the colors. These are a small sampling of the colors that you can get the fan in if you want it anodized. Other cool colors that we've had the fans done in. One is a Dayglow orange. The purple. It's kind of like almost close to royal plum. Really bright green. A few different shades of gold. And unusual is that there's like a silver anodized, and I think that's what this one in the upper left hand corner is. I don't talk about quantities. I want to keep possible competitors off balance, but I'll say it's been a way more popular fan option than what racers are using right now. I'm really proud of it, but I just keep that stuff to myself.
Hey, Kevin, did you see the question regarding what it's made of?
Yes, this is 6061 T6 machine from Solid.
Okay. And I think you have one more. Let's see. I think we're done with slides. There we go. I just want to point out to everybody to write down his email address if you have more questions, and work back with Kevin through email. And I think this is
How
the
do we
best
do
way to
on
get hold.
time?
You're doing good. We're going to ask questions now. That's the best way to get hold of you, right, Kevin? Through email?
It makes it easy. I'll get back with people right away. You won't be waiting a week to get a reply from me. I'll get her done within a day. Typically it's the same day, but I'm pretty quick about getting back to people.
Okay, so there's a question here regarding with additive manufacturing materials becoming stronger and more economical, is a 3D printed version in the works?
Probably not, at least for now. It's been really clear to me that for stiffness reasons, the fan really needs to be a metal fan. The good reason that the mag fan was made out of mag instead of plastic. The if you make it from plastic, you have to add so much material to make it to make it be stiff enough. Um, Even if it can handle the heat, they end up being heavy. There was, everybody probably knows about the Delrin plastic fan. And they got that out of production really quick once they found out that it was making formaldehyde. What a lot of people don't know is that they went ahead and redid it out of nylon. And I saw one of those fans, and although people say that it was exactly the same thing as the shape of the ag fan, that's so far from the truth. They had to beef that thing up like you wouldn't believe, and there was so much extra plastic on it. It weighed 1.7 pounds, and so the reason for making it out of plastic didn't achieve their goal. And typically what ends up happening, that's just a typical example. Anytime you want to make something from plastic, if strength and stiffness are a consideration, you go to magnesium instead of try to make it big enough out of plastic. It'll end up being too heavy, so much material will be used, it'll be too expensive. When you get to carbon fiber, basically if you build the fan up enough to handle to be stiff enough, it's about 50 hours of print time. And if they're giving away their time, sure, I'd love to be able to give away my time and get rewarded for it, but I can't. They got to pay for their machine somehow. Um, 50 dollars or 50 hours of print time at $100 an hour, which is super cheap for one of those kind of printers. You know, $5,000 for a fan? Oh, I don't think so. It's so far out of the ballpark. It's silly. Fan and those kind of fans are out of. They have some other issues with reliability. You're basically babysitting those things after they get in the engine. Next.
Okay, shrouds always seems to be a question, and I know I got a couple in email, but I'm also going to read the one that's here in chat. It's the same question. What's the downside of removing the lower shrouds? I've also got questions. Is there a benefit to removing the lower shrouds?
Oh, okay. So first, the downside of removing the lower shrouds. The warm-up takes longer. It's not too big of a deal if it's 100 degrees outside. The warm-up function is not that bad, but if it starts getting cold, a little cooler than you want, if say it goes down to 75, the warm-up is just awful. The other thing, you don't really want, or you want the oil to get hot quick, because it's that way it can boil off gasoline and water that gets into it. And cold oil definitely is not good. The other thing about taking the lower shrouds off is that it makes the fan use a whole bunch more horsepower. If you need to, and it really does increase the flow a bunch. The best I could tell, the airflow increase that you get from doing that is on the order of 30%. So especially for the stock fan that doesn't deal with pressure maybe as well as it should, that's how you get the cooling to be pretty good. But I wouldn't do it unless there was any better way of getting around it. One right at the end of last summer, I tried it and didn't get around to putting the lower shrouds on. When I got down to 60 degrees, I couldn't get the head temperature above 220. That's about right. It's 80 to 90 degrees. Typically stock 140, they get up to around 390, flat level ground at 80 degrees out. Take lower shrouds off and it goes down to 300. But if you got a nice tight fan gap, you don't need to do it. Buddy of mine knows all about this, so go ahead.
There you go. Well, that's a good stopping point in terms of, you got a good fan, you won't need to do that, right? So
Exactly. Not maybe
Alright.
not as much. When it's 100 degrees out, yes, it does help, but with
Good
mine, it kind
point.
of goes the other way. All that extra flow and the horsepower usage goes down some more.
All
So it's
right,
an
well,
inverted
we're a
relationship.
little over the top of the hour, so I'm gonna wrap this up. And again, everyone should have Kevin's email address, so you can, of course, email him your
Yeah,
questions and also get more
I'll
information
answer them all.
about the
I'll
fan.
answer them all.
He's done an
Yeah.
awful lot of work on this. And again, thank you to the folks at the performance workshop who came and said this would be a really interesting meetup. And it has been, because I've learned a lot about performance and cooling just working with Kevin over the last day or so on preparing for this. And I hope everyone else on the call has too. Kevin Nash, thank you so much for attending and bringing us this information.